So much like a programming language, you can write a program in some programming language, but that is obviously contingent on a way to interpret that programming language, right? You're expecting that program to be used in a particular way to do a particular process. And so what we need to do now is formalize that. Again, for the third time, we've already done this a lot. We've already more or less done this. We just need to be more specific about how it's going to work. We need to specify some kind of, what do you call it? Well, you'll see. So now moving to 2. Semantics. We've already done most of this. So suppose we have a Turing machine M. We want to be very clear about how it starts and how it stops. That's kind of the main thing we still need to do. About how it starts and how it stops. So we kind of want to standardize that. That's pretty much all that we still have to do. So we're assuming infinite paper. So I'm just going to type the rest of this. So we're assuming infinite paper. So this really implies an infinite grid. So we're assuming infinite paper. Oh, okay. So we're assuming infinite paper. But let's mark something the origin anyway. Let's mark something as the origin. You can kind of think of this as the top left of a particular piece of graph paper, right? I'm allowed to keep going up and left more, but let's just pretend, right? So I'll pick some point to mark the origin 0, 0. Right? We also let's also mark an initial state. So let's also designate an initial state, which I'm going to call it like QI. And QI is the and so an initial state basically says QI is the mental state saying I am at the beginning of the computation, right? Oh, and I should have also mentioned that this origin is going to be the initial point of focus. And that's why I'm defining it. So there's going to be some location on the page where I'm always going to start the computation, and there's also always some state in which I'm always going to start the computation. So I've kind of specified an initial configuration of the machine up to like whatever I'm putting on the page to start. So from here, we sort of have, given a Turing machine, we can kind of simply go. So let me go ahead and kind of summarize this up. So we're kind of almost done. From here, given a Turing machine, we can simply go. Oops. Initial context yields an action, yielding a new context, yielding a new action, etc. Eventually we might encounter a halting state. So eventually we might encounter a halting state. It could be, and in that case we stop. And then so I've kind of fully formalized, to the extent that we need to formalize it, what a Turing machine is and how it theoretically works. So let's do an example. So example. Let's make a Turing machine which, let's say, adds two numbers. I want to show you how easy this is. Lots of people think Turing machines are like super arcane and confusing and weird. And honestly, if you do the normal thing that people do, which is not consider graph paper, but only consider like a single row and call that tape, then it can be kind of confusing. But we don't have that problem. We've got graph paper. And so we can pretty easily, naturally just describe any algorithm for graph paper with a Turing machine. So here's my graph paper. And let's say I want to add like 378 to like 42. And so I'll start things off here. And so let's go ahead and say the origin is like, I should probably make this actual graph paper. So I'm going to need to keep some space at the top for carry bits, right? So let's just say this is like 378. Wait, I just said I needed space at the top for carry bits. So let's say 378 and 42. And let's say that this is the origin. So I'll mark in green. So this is what I'll mark as 0, 0. And I'm initially in state QI. And so let's just say this is it. We don't need lines. We don't need a plus sign. But you know what to do, right? We're going to need to map. So what I'm going to need to do is, here's what I'll need to do. Let's go ahead and describe it. Because again, we are somewhat limited, right? We can only move around in discrete steps. So what I'm going to need to do generally is, I'm going to call this step 1, but it's really not a step of the computation. It's just kind of a step 1 conceptually. What I'm going to do is I'm going to move my focus up twice, changing my mental state according to the digits I see. So basically what I'm going to do is I'm going to basically like, so step 1 is I will be in the mental state like blank, and I'm going to typically denote blanks as like these kind of square cups. So I'm initially in the state like blank and then QI, the initial state. So what instruction do I want to do? Well, I just want to move up. And then I'm going to move into like a, and so I'm going to move up. I'm going to leave it alone, so I'm going to leave it blank. I'm not going to write anything there. So I need to specify 3 things, right? I need to specify the symbol I print in this cell, and I need to specify what direction to go in, and I need to specify a state to shift into. I'm going to go ahead and turn into some state QU for moving up. I'm going to I'll call it Q, I don't know, I'll call it Q1 because I'm lazy, and then I'm going to go up. And so that's going to shift me up here. Now I'm here. And so what's it going to do when it sees this? So now I'm looking at a 2, and I'm in state Q1. What should I say to do at this point? Well, Q1 is always going to be in a state of moving up, right? That's what Q1 means. Actually, I think I will say QU, because I'm going to do something here in a second. I'm making this up as I go. I didn't like come up with a kind of plan on explaining this. I just figured it would be really easy because it is. So 2 and then QU. What I'm going to do is I'm going to remember the 2 here. So I don't want to do anything with the 2. I want to leave it alone. But I am going to shift into a state that remembers that I saw 2. So I'm going to shift into state Q2U. Just make a state for that. And then I'm going to go up again. And then I'm going to be here. And so what I'm going to do there is I'm going to be looking at an 8, and I'll be in state Q2U. Or, you know, by the way, this could be state Q2U, it could be state Q3U, or Q4U. It could be, it's just going to be whatever digit I saw the first time. Saw in that first step. And I know I'm at the top because I'm in Q2U phase. So what I'm going to do is I'm going to remember I'm going to leave it alone, just like before. I'm going to remember that I had the 8, so I'm going to shift into the state Q28, and then I'm going to go down again. And so that will take me back down, and then and I want to go down twice. So so let's just say that if I'm in any Q with 2 digits state, so basically I'll just specify the instruction this way for now. If I'm looking at something, and I'm looking at like Q with 2 digits here, I'll just say like Q like A, B digits. What I'm going to do in response to that is I'm just going to leave them alone. Same thing. And then I'll shift into QAB minus. I'll just put it like that. And this says I'm in a new state where I've shifted down once and I need to shift down again. Actually, I don't need to do that. What I'm going to do is I'll say it this way. I'm looking at like the position. I say anything here. I'm going to say anything not a square, a blank. If it's not a blank, then just keep staying in the same state. Don't print anything new. Don't erase what you have there, and then just keep going down. And then keep going down until you encounter a blank, because by the time we've encountered a blank again, we're back where we started here. And then at that point, I said this is step 1, but I'm just kind of going. And then at that point, I have the information that I needed. I got down back to the blank. I'm looking at a blank. I'm in state Q28. And what I'm going to do there is I need to add the 2 numbers and print the result here, and then I also need to carry a bit if I need to carry a bit. I'll just assume for simplicity that I'm always going to need to carry a bit. The bit might be 0. So I'm going to print 8 plus 2. I'm going to print a 0 because that's 8 plus 2 is 10. So put the 0 here, and then I'm going to start moving up again. Actually, I need to go. I'll shift into. I need to carry a bit, so I'm going to say like Q1 left, or Q1. I guess that's all I need to do is just say Q1. And then I'm going to go. I don't know, left, or left and up at the same time. So I'm going to print the 0 here, and then I'm going to move over here, and then I'm going to be in a state Q1. The one here is to mark that I'm carrying a bit. And then at that point, what I'm going to do is I'm going to be at a state like I'm looking at a 4. I'll be in Q1 as like my kind of state, and then I'll shift that into I want to leave the 4 alone. I want to stay in state Q1, and I want to move up. And I want to do that twice. And so you kind of see what I'm doing. I'm going to move up twice, and then I'm going to put the 1 here, and then I'm going to move back down. And as I move back down, I can remember the state, the numbers that I see in the same way, just using states. And then I can put the sum here, and then I can move left again, and then I can move up, and then I can put the parity bit here, and then I can move back down, and then I can put the 0 here, and you get the idea. All you're doing is describing addition in like a very mechanical way. That's all I'm doing. Normal addition, normie addition. That's it. So that's essentially what we've done. Is we have mechanized the process of human computation. I hope I've convinced you of that with this example, and I would encourage you maybe to write out all of these instructions. Maybe write this out in more detail. Like finish this example yourself. I'm not going to obviously do it here. But I hope I convinced you, showed you that this really is just kind of a formal, it's a mechanization of human computation. Now the last thing I want to do with this video is I want to standardize inputs and outputs. So last thing to do is standardize inputs and outputs. So I didn't have a standard for inputs and outputs here, but the standard is going to be this, just to kind of have a standard. Here's my graph paper, and I'll just say for simplicity that this is my origin. I'll mark it in green. And basically, I want to be able to talk about inputs and outputs, right? So the output here would be, so 7 plus 2 is, or 7 plus 4 plus 1 is 13, so I'll put the 3 here, and then the 1 here, and then this will be a 4, so the answer is 430. That doesn't sound right. Oh, 12. 420. Blaze it. Nice. That was completely unintentional, by the way. So anyway, so to standardize inputs outputs, what I'll do here is I'll essentially say the input will look like this. It'll look like a string. 3, what did I use? 37842. And then I'll allow for a comma as a symbol. So it'll look like this. And then maybe I'll have to implement some kind of initial subroutine where I set up the addition in the way that you normally see it. But basically what I'm going to say is that input will be a single row string. Remember, a string is a sequence of characters. And it'll be written like this. So this is how every Turing machine will start. Everything else will be blanks. Everything else is blanks, and if the Turing machine stops, which it doesn't have to, there's no guarantee that it will, call what's written on this first row the output. So what I would do essentially to kind of formalize what I did up here, or standardize what I did up here, is I would take the 420, I would, so basically the steps would be basically like, I would start out with 378, 42, and then I would essentially write it out down here, and then I would crank through it, and I would get 420, and then I would put the 420, I would erase this, and I would put the 420 here, and then I would halt. And so the answer would be written always kind of at the same place that the input was. And so that is that's the way I'll standardize inputs and outputs. If the Turing machine doesn't halt, so if y is the string when the machine halts, when m halts on the input x, then we'll write that m of x is equal to y. If it doesn't halt, if I never enter a halting state, which is entirely possible, then we write that m of x is equal to just a sideways arrow like that. So it always equals something. It just might equal this weird DNE like error thing. So that's it. That's the standardization. That is the kind of the mechanizing of the process that I described in the previous video. Obviously, this is going to be its own video now. So that was the boring part. Now we can talk about the Church-Turing thesis, but I'm going to leave that to the next video. And now we're going to start to get fun, to have some fun, I think.